I did in class. And so mine is quite content heavy, but I think it is quite interesting. So I'll first start off with applying mathematics to the real world. And this is what I did in Math Apps. So they covered something called APs and GPs. So if you guys remember what APs are, they're just number sequences which are, this is an example, 2, 4, 6, 8, 10, 12. So basically you have a starting value and a constant value that increases. And a GP essentially is 2, 4, 8, 16. So something like this, a starting value, but this constant ratio. Usually kids can manipulate the equations. They might have some difficulty with the algebra, but this is quite not applied, essentially. So the way I wanted to link APs to the world was showing them the height of the world's tallest buildings. And essentially over time, the height of the tallest buildings has increased. And it's increased by this value that looks something like an AP. And I asked them why. And they couldn't figure out why until I told them, think about this. You're paying billions of dollars to build a building, and you find out the world record's just a few stories above yours. You're going to push the engineer to just push a few stories above that world record. Then a few years later, someone else builds another building, and they're going to push the engineer to build something else a few stories higher. And it just goes up, just by that constant amount. Even though the buildings are much taller, they're just adding on a few stories. They're just adding on a few stories. It's not trying to double the guy before, it's just trying to add on a few stories. Yeah? So this is kind of like your AP. However, here, there starts to be, there's a discrepancy. And I try to get them to explain this. And they couldn't figure out why, other than the fact that these are all in America and these aren't. So architecture sort of kicks in at this point. But the actual reason why over here it starts becoming really crazy is because somewhere about 1950s or something, TVs became a really big thing in households. And the tallest structures in the world turned to be, they weren't actually buildings anymore. They were TV antennas. So at a certain point around here, the tallest structures weren't buildings, they were antennas. And then the Sultan of Dubai said, I'm going to build a building which is taller than the world's tallest antenna. So that's why it just went up.
Okay.
And that's where the anomaly kind of comes in. But generally here, you've got this starting value, but this constant value being added to it. And this is AP being applied.
Cool.
So now going to GPs, I think I've told Rowan before, right? But what is the number between 1 and 9? So if I ask you guys, what do you think the number between 1 and 9 is?
5.
You think it's 5? 5?
It's 5.
5?
6, I'd say 6.
5?
Implied
6?
halfway.
Yeah,
Okay.
I rounded up.
A whole number?
Yeah.
Yeah, I kind of rounded up.
Good 3.
So
I
we're
don't
saying
know.
5 because
4.
4. Well, most people will say 5 because 1 plus 4 equals to 5. And then 5 plus 4 equals to 9. And that's why it's like that middle number they picked. But there's actually a tribe, or there's a few tribes in Papua New Guinea and a few tribes in South America which say the answer is 3. Can you explain why? Is this bizarre or is this?
3 times 3 is 9.
Yeah.
That's the
They're using
sequence.
it. They're using it like a GP.
Like
So to them, this is more natural. To someone like us, who's actually done mathematics formally at school, this is more natural. And I'll explain to you why the second one is actually more natural to someone else, like hasn't actually done this kind of schooling. So I have a slide here. This is slide A. I don't want you to actually count the numbers. I'm going to show you a few slides. But I want you to tell me which slide has more dots? So A or B?
The obvious is B.
The
There's
obvious
got
is
to be a
B.
trick.
Obviously it's B, because you can kind of tell straight away, it's just so instinctive.
Yeah.
Okay, C or D?
D.
So it's D, C,
Same.
C
Same.
looked to be more credible.
C. C had 10, D had 9.
Ah.
Okay, so even though there was this small increase or small decrease, at the value of around 10, it becomes really hard to notice.
Yeah.
So imagine you're a hunter, you're trying to hunt down a herd of 100 animals. Doesn't really matter if it's 101 or 100. No, it's a herd, right? So that's why to them, it's just natural that it has to be this ratio of numbers. And it's demonstrated more clearly here with D, E. When I've doubled it, it's just so obvious. It's kind of like my A and B again, where it's just doubled.
Mm.
Okay, so that's GP being applied and how it's very natural for those tribes people to think 3 is the middle number.
So you're thinking multiple, like
Yeah.
multiplying rather than adding in
Yeah.
groups.
Yeah.
So Tony, can I ask what G might stand for as opposed to?
Oh, geometric.
Geometry.
Oh, yeah, I wonder what AP and GP.
Arithmetic and geometry.
Ah, how do you know that?
Okay, and then now I'm going to apply both of these together to the world, and I'm going to plot a graph. This is just some kind of arbitrary or scaled units, so this some kind of units, and this is time. And a very famous pseudo-economist slash philosopher named Thomas Malthus basically argued that population tends to increase geometrically because, for the past, let's say, 50 years, the human population has gone from about 2 billion to currently 7 billion. And before that, or maybe before the Industrial Revolution, it's been less than 1 billion till the beginning of time. So the population basically increases really quickly. That's a geometric progression. And he also argued that food production increases, but because land is limited and resources essentially are limited, it doesn't increase anywhere near as fast and is approximated by our AP. He argued that there is a point here that once we cross that threshold, depending on your scaling of units, resources will be less than demand. And after that, it's the cause of suffering or it's the cause of war, etc. So this is a problem in the world because we need food. So what could we do to fix this problem? One thing, clearly, is to change the population growth. So we can look at policies such as in China, the one-child policy, that basically shut down population growth very quickly, but that's near impossible to pass in a democratic society. Then you look at cases like India. They had a policy where they paid people money, or guys money, to get vasectomies. And the people they were drawing in tended to have already have kids, and as a consequence, it wasn't a very effective program. So they abandoned that, and they passed a very extremist policy, which was repealed very quickly, which was, if you go to jail for anything, you get a vasectomy.
God, you're gone.
So you go to jail for drink driving, you wake up, you get a vasectomy. That led to protests.
Yeah.
That was repealed really quickly. So essentially, in a democratic society, it's near impossible to control population. You can do it by educating people. For some reason, there's a correlation between literacy and population growth. But other than that, you can't actually force them.
The other thing you can do is have disruptive change.
Disruptive change.
Change to the arithmetic progression of things like resources. For example, take oil in the world.
Yeah.
Okay, that's classic to this kind of curve.
Yeah.
But then you'll have a disruptive change where you come off oil and you go to another source of energy.
Yeah.
So you don't follow an arithmetic curve, you'll actually follow it becomes more like a series of steps or step-ups and step-downs.
So that's what the next thing I was going to say.
Oh,
So
sorry,
we
did I
don't
jump ahead?
we don't change the population, we can change...
Correct, and it's usually through a disruptive change, which is a more radical change. You know, like a different technology or like food production. Instead of farming, I don't know, you make it in labs or something. But there's a disruptive change to the technology for whatever controls the arithmetic progression of the resource.
Yeah, that's true. So I talked about the Green Revolution, because in the 1970s, a lot of the farming techniques like using tractors and basically petroleum kind of farming was moved to India, and their grain production increased tenfold. So essentially, at some point, it just went up. Yeah, so you can, in current times, you've got GM crops or whatever, so you've got all these different policies or ideas you can kick in, which changes this AP right here. So you can link this to the world. So that's basically my first point of applying maths to the real world.
But at the end of the day, in a real world problem, you need both solutions.
You do.
Something to interfere with both graphs.
Can you
not
just
to
swing and pull them
prolong,
together like
give
that?
yourself more time to think of a good way to interrupt GP.
Yeah.
Yes.
The next thing I want to talk about, I was just going to show two videos, but it kind of links both ideas of physics and math, and it's the idea of generalization of a simple concept. So, in maths, generally when you have a very simple solution, you try to get to... Is there a volume for this?
Yeah, we've got to unmute it. I think on the bottom, maybe. Oh no, it's not.
Oh, on the side of the board
Good, so
Alright.
is the volume.
Can you see it?
Physical knob or something.
I see the knobs, but I don't see a button.
is there a little
No, it's
Just
not.
turn the dial to the
Turn
right.
dial. Yep.
It's on max.
is there a little white button that isn't glowing?
No.
Is it glowing? Yeah.
Yeah.
Oh dear.
What about the on the YouTube little volume thing? Not that it would be down because the equalizer's
Hang
going.
on.
I can hear pitch. Something going crazy.
Essentially,
Yeah.
let's pause it for a sec. So essentially, in mathematics, you have a very simple solution which, after you derive it, you try to generalize it to a higher dimensional problem or more variables or an added degree of freedom. And that occurs in physics as well. You just try to take it to the next step, generalization. So this is something I did in...
Where's your pen?
This is mute off.
You want me to know?
You
No,
want
you
your
can't
box?
use that for that.
Okay. My
In
bad.
physics, you have a similar thing, and I did. I basically talked about this when I talked about waves and optics and stuff. But I start off with waves. Essentially, this is a Rubens tube. It's a one-dimensional tube where there's gas burning in it, and you light a flame, and then you play notes, and these waves appear. So this is how you can visualize sound as a wave. Okay.
Play notes, how? Sorry, I don't.
You just play it in a room. The
Oh.
moment the sound passes through the...
Oh, as soon as the sound waves, you mean pass
Yep.
over. Oh, okay, sorry.
This gas will just burn in
Yep.
this wave. And then if you play music, so you get
It's
different
like an
frequencies.
equalizer.
Yeah. Equalizers, basically the mathematics behind them is also to do with sines and causes, so it turns out to be waves as well.
Wow.
So you play it very nicely, a simple sine wave or
Yeah.
something.
And he's playing rock and roll now.
So what happens to your cathode ray oscillator if you put sound
Yeah,
through it? Like
yes.
Yes.
Yeah.
Do we have a Rubens tube?
Oh,
No,
we
we
don't,
have
and they're very dangerous as well.
Oh,
Yeah, we probably gas.
right, forget it then.
Burning gas.
You can do similar things with other technologies.
Yeah.
So generalizing to the next dimension is a board which has basically gas coming out of it, burning it, and then playing notes. So
Oh, yeah.
That's cool.
as he's playing higher and higher notes, different regions basically start appearing. And as he doubles it, the regions double as well. So it's kind of the same thing as that, but
But yeah,
Just higher
3D,
dimension.
yeah.
so that's another kind of harmonic. And he keeps doing that, and then he plays music forward. And it's like,
Reminds me of the slime on the non-Newtonian fluid on the speaker, how it moves in different sort of ways to the vibrations.
yeah. But this is to generalize that one-dimensional thing to a two-dimensional thing. And then an example of three-dimensional thing, which I can't actually show, would be essentially like a star. Because stars are basically balls of gas on fire, oscillating in 3 dimensions. And what I like to say to the kids is, think about how beautiful the song is, but you can't actually hear it. But they can imagine these regions moving in such a complicated way.
But the sun does oscillate every time.
It does.
Changes,
It's just,
So what is
reverses the
4
magnetic field
dimensions actually hearing it
and sunspot cycles.
and feeling it?
3 dimensions is still, you can still hear it. Like, I mean, but it's just that the moment you get there, you die.
Yeah.
You can't physically be there.
No.
Yeah.
Cool.
So that's my idea of generalizing something from a very simple thing to a much more complicated thing.
You're a bit trippy, Tony.
My third idea, which is very heavy in physics, is to do with connecting very distant ideas together. And I'm going to use the content knowledge of circuits. So current is usually defined as charge over time, and voltage is usually defined as the potential difference across an electric field. And yeah, so kids kind of get these definitions. They know how to do calculations, and after this, there's a lot of calculations they can do. They can solve them, but they get to a situation like this, where they can't do it.
Rub it off the whiteboard.
So imagine halfway through a calculation of their circuit, they've got a situation where there's 9 volts here, 3 volts here, and I ask them, what's the total voltage across this part of the circuit? And they can work out, okay, it's 12 volts. Makes sense. But the moment I add in another resistor next to it, and I ask them, what's the total voltage? They can't really get the right answer. So, do you think it's more or less?
Still 9 volts.
Yeah, I thought it was still 12 because you either
It's
have
9 plus the 3.
you have the upper
Yeah.
parallel,
Still 9 volts on the left because
parallel
you've still got
or-
the same potential across the two.
Yeah. But the kids don't seem to get that.
Yeah.
Right?
Ah.
If you add another resistor there, they think it must change the number somehow. It must change the number. You've changed the circuit.
Doesn't that just tell you that their understanding of series and parallel isn't concrete? Like they don't get that understanding.
Well, I think it comes back to not understanding this properly.
What it actually means. So they can calculate and put numbers into it, but they don't actually know what it means.
Yes, they don't know how to relate it to the real world.
Yeah.
It's just an equation.
Yeah. So they can do this, but this doesn't seem to be obvious to them.
That's interesting.
So, so basically there's this idea called the water analogy of electricity, which explains how electricity flows. And this is one example of a computer that runs on water. It's used to simulate the economy back in the very old days. Right? And the volume of water per second is actually the current. And the pumps which control how much the water, how much water flows, the pumps is basically controlling the voltage.
Yes, the potential.
Yeah. Except
the best thing with potential is to have a tank up at higher levels.
Yeah.
That's a better way of showing potential energy than really a pump. But
yeah. But the thing is, I would really like to build something like this to show the kids. So what I built was.
You got to go back to select.
Okay. No mind. So what I built was a 3-bit adder that works in Minecraft, a game that they like to play.
Do you play Minecraft, Mike?
It's supposed to be very good for problem solving.
Yeah. Tony's an expert at it, and as you can see, how he just thinks so abstractly.
Yes.
I might just turn off the light.
So I think the time I wanted was 4 minutes.
Am I doing it?
Yeah.
Create your own little Minecraft world.
Does Pat do it?
No, it doesn't.
No.
I think it's something we should
Okay, so
I think so. If they're going to play a game, play this.
Yeah.
basically you stand here and then you select any 3-digit number. That's binary, of course. And I think I selected 1, 1, nothing. So 1, 0. 1, 0, 1. And I basically let the lava, which is my water in this world, flow. And I basically, the way it flows is basically how the current flows or computer really calculates in a sense. And as Rob was saying, the potential difference is the height. So in the Minecraft world, there is no electric field. There's only a gravitational field. So the height, the potential difference in the gravitational field is technically the voltage. And I actually can show you that certain switches require more voltage than others to work. And then basically it just goes through all these switches and it calculates the sum of it. And I talked for a really long time about how this thing works. Down here there's a shadow. So there's a 3D kind of circuit where it goes up, where the voltage is kind of vertical. But the shadow being cast down, it's kind of like their little breadboard that they work on, this flat thing. So, I don't know, maybe they can imagine that the flat thing they're holding is actually this 3D thing and that's actually there.
Yes.
Yeah. So I talk about that and then eventually I say that's the microchip because that's what you're actually seeing in real life, but that's what's actually going on.
Above it, in another dimension.
Yeah. It's not a real dimension, but it's, you can imagine as an analogy.
Of it,
Kind of like the Matrix, you know, people are actually
Yes.
controlling the real world from the Matrix.
Yeah.
I should sit in some of your classes too.
Tony's brilliant.
Given that I missed the entirety of year 8, 9, 10 from high school.
Did you?
Yeah, so I think it's really beautiful the way it flows. Sometimes I just stare at that and just,
Get inspired.
Wow.
Yeah. And then to take this even further, I basically connected it to, that won't work either, I have to go back to the photo. Connected to something that Heron of Alexandria did. And he built a miniature television that ran for 30 minutes back in the Bronze Age or something.
Oh, wow.
He basically used rope. It basically fell down at, it was pulled down because of gravity, so the voltage is still that gravitational field, but instead of it being water, it was a rope. And the rope was wrapped around a stick at different points, and that basically, 6 minutes. Okay. So there's this puppet thing, and these puppets come out at different times, they move at different sequences, backdrops move, they switch around,
That's cool.
instruments play, and then you have sound effects like thunder and stuff, and it goes for 30 minutes. Everything happens in sequence.
And it's all automated by this rope.
Dropping.
Dropping.
This dropping rope that's wrapped around a stick, and you could wrap around different parts of the stick and different digital
It's
codes.
just coding.
Yeah, so he was the first programmer.
Oh, that is so cool.
Yeah, so that's like extending that idea. Instead of, you don't even have to have water, you can have a rope.
Yeah.
Yeah,
You can do
and
something.
it's meant to move, I don't know why it stopped, but okay.
Yeah, it's still loading probably.
Well, the reason why that connecting these ideas is so important is because in real life, scientists actually do connect really weird ideas and put it together. So,
Well, scientists create the view of the world through models,
exactly.
you know, and it's how you can bring those models to the kids is how you capture them.
Yeah. So this is an example I used when I was teaching circuits. So when you're talking about things like resistance or conductors versus non-conductors, you're actually using a model called the free electron model. I'll just use free electron model. And that is actually created through two really seemingly unrelated ideas, but very simple ideas. And what they did in history was they got this idea of lattice theory. So because they thought, you know, these nuclei are repeating in this regular structure. Let's just use the mathematics of that. That's pretty well understood, because if something is periodical, you just fit true to it. And then they said, well, let's just say the electrons are just moving around. What's the simplest thing we can say about things moving around randomly? Gas laws. So these electrons are actually just clouds of gas. Like that's all it is.
Well, behaving similar to gas
Yeah.
particles.
Is it actually doing that? Not really, but this is a very simple idea.
They have plenty of free
Simple idea.
space to move in electrons.
Yeah, but
There's
it's
so much
actually,
space between the atoms, relatively.
yeah. So this is like
But they do
very
move in
approximate.
defined fields.
Very approximate. But with these two ideas that seemingly are completely unrelated, they bring it together and they produce the free electron model, where we get our ideas of these metals, the electrons want to move across, and the non-metals don't, hence they can't conduct heat as well as current and that kind of stuff. All the properties is derived from these two unrelated ideas. Yeah, so connecting these distant ideas together produce new bodies of knowledge. And so I basically want to finish off. So, you know, that one theory or that one equation that you're learning, it might not be important. You might not actually be asked to do that question ever again in your life. But the fact is, if you have internalized it, then it should change your way of thinking forever. And that's how you come up with all these weird, crazy things. And that's what we should be aiming for.
Yeah.
And hence, with those application, connecting ideas and generalizing it leads to creativity.
Yeah.
Thank you.
Awesome.
Yeah.
Yay. Why don't we start tomorrow now? I want to go to
now.